Hello, we will now start talking about contents of the universe, and we'll begin with the regular matter, the baryons. First, let us recall what we learned from the cosmological tests. What are the density parameters associated with different components that we see in the universe? We know, largely from the precision measurements of the cosmic microwave background, that the universe is very close to flat, if not absolutely flat. That is, that omega total is equal to 1. The total matter energy density is exactly equal to critical within some very small deviation. We also know from dynamical measurements and microwave background, and some extent supernovae and other reasons, that the density parameter of all matter in the universe that exercises gravity is about 0.27. And we know that the total density of baryons expressed in units of critical density is only about 4.5 or 5% of the critical density. As it turns out, luminous matter, stuff that we actually see in galaxies as stars or gas, only adds up to about 0.5%. And so therefore, looking at these simple inequalities, there are implications. Because 0.5% is less than 5%, there must be some sort of hidden or missing baryonic matter. Because 5% is less than 27%, there has to be some kind of non-baryonic dark matter. And because 27% is less than 1, there has to be a dark energy. So let's look at the luminous baryons first. Those will be mostly in galaxies. And the way to do this is to integrate them spatially. That is, what we need is a distribution function of galaxy luminosities, also known as the luminosity function. We obtain those from redshift surveys that measure distances to nearby galaxies, and then we simply add up the light in a volume in which those measurements are complete and average them over. The results from different redshift surveys are all in very good agreement and amount to about a couple 100 million solar luminosities per co-moving cubic megaparsec locally here now for a Hubble constant of 70, which is close enough. But we want to find out how much mass is in those stars, and for that we need so-called mass-to-light ratios of stellar populations. Stars of different mass at different ages produce energy at different rates, and so we have to integrate overall production of light for a stellar population at a certain age, or a mixture of ages, and see. And so here it is for a variety of galaxies of different Hubble types, and by and large it doesn't change a lot. For stellar populations we see in galaxies, it's of the order of 4 or 5. That is, on average, stellar populations are less efficient in producing light per unit mass. And the reason for that is that there is a lot of mass in very low mass stars, which are not very good light producers. You probably recall that more massive stars are far more efficient in producing energy. Now, these measurements do include a little bit of dark matter, but it's not really important at the level we're talking about. Because the more massive stars are far more luminous per unit mass, and because they live shorter. The age of the stellar population plays an important role, and those that are dominated by younger stars will be more luminous per unit mass. Also, this will depend on the bandpass, because most of the light produced by luminous stars in ultraviolet, then bluer bands will be more affected by star formation than the red ones. And the flip side of that is that blue light is more susceptible to extinction by dust, so the corrections for that have to be made. So we add it all up, and we find out that the density of the material we actually see in galaxies is little less than 1 billion solar masses per co-moving cubic megaparsec for favorite values of Hubble constant. Converting that into grams per cubic centimeter and dividing by the critical density gives us the omega in visible stellar populations, and it's only about 0.5% of the total. This is quite a remarkable result, actually, that all the stuff that we see out there adds up to less than 1%, only to 0.5% of all the matter energy that there is in the universe that we know from other reasons. But how much should we see? And the answer to that is in measuring of the total baryonic density, which you probably recall is done in two very different ways. One is by measuring abundances of deuterium or other light nuclei in the intergalactic clouds at high redshifts. The deuterium is the most sensitive of those, and that produces a result of the order of 4.5% of the critical density. A completely different approach based on different measurements and different physics is from acoustic oscillations in the early universe from cosmic microwave background, and that produces a result which is in perfectly good agreement. So because of that, two completely different ways of measuring it yield the same result, and it's repeated again and again. We believe that indeed we do know that the total baryonic density in the universe corresponds to a density parameter, omega baryons, of about 5% or a little less. Where are the remaining 90% of the baryons? Many suggestions have been made, but essentially it boils down to three different kinds. One possibility is that they're in form of some optically dark objects called machos, or massive compact halo objects, which could be of different physical nature. Could be brown dwarfs, that is dim substellar objects, could be planets, could be even gigantic comets, could be black holes. This is not known, but there are ways in which we can test that. As we will learn later in the class, this turns out not to be the viable possibility. We've done measurement and we know that. The second possibility is that these missing baryons are in the form of very dense, cold molecular clouds. This is a little bit ad hoc because we do know about molecular gas in a galaxy. This will have to be a completely new component because these clouds will be very small, they'll be very hard to detect. It's cold, they will not emit much light. It's a legitimate possibility, and people look for it, and so far there doesn't seem to be any evidence for such a thing. The final possibility, and most likely the correct one, is that these baryons are in form of hot gas bound to galaxy groups, simply corresponding to the large-scale structure. Because of the virial temperature equilibrium, it has to be balanced against whatever the gravitational potential is. The expected temperature of this gas is of the order of million degrees Kelvin. So that's not as hot as X-ray gas in clusters of galaxies. The predictions are made by numerical simulations of structure formation, and it's a perfectly reasonable thing to expect. Now the problem is that the gas at that temperature emits primarily in hard ultraviolet or very soft X-rays. And those wavelengths are very effectively absorbed by interstellar hydrogen. Our galaxy has an atmosphere, interstellar gas, mostly neutral hydrogen, and because that absorbs light on these wavelengths, we cannot see this gas. This is same as looking through Earth's atmosphere that absorbs UV radiation due to the ozone layer, or in infrared, there are bands of molecular water absorption. So since we cannot get outside Milky Way's atmosphere, we are doomed not to see this gas, which is a little bit of a joke of a nature that most of the baryons in the universe are hidden from us by the hydrogen fog. However, there is a way to discover it, and that is by absorption. Let's now take a quick look at some of these possibilities in turn. First, the possibility of machos, massive compact halo objects. If we look at distribution of stellar masses, it is a very steep power law that there are many more low mass stars than there are high mass stars. And because stellar luminosity scales roughly as the fourth power of stellar mass, that means that the faint end of the luminosity function would contribute least amount of light but most of the mass. And the critical issue is where is the cutoff, if any, at the low mass end. We know that stars with masses less than about 8% of solar cannot fuse hydrogen into helium in their cores, and those are the brown dwarfs. So you can pack a lot of mass in these substellar objects without them producing any observable visible signature. You can go as far as you want down the mass function, or there could be additional peaks. There may be interstellar planets or interstellar slush balls and comets. They'll be very hard to detect. But there are ways in which we can test some of these possibilities. Well, first of all, good thing is that we know that brown dwarfs do exist. They've been discovered almost 2 decades ago, and by now we know thousands of them from various near-infrared surveys. So we know fairly well what that population is like. And the answer is, there isn't enough of them to account for the missing baryonic matter, let alone the rest of the dark matter. So the most viable possibility today, the one which most astronomers believe, is that most of the baryons are in form of this hot but not too hot gas, which emits radiation that's effectively absorbed by the by the interstellar medium in our galaxy. But we can detect it in absorption because of its physical state. Absorption lines of elements like oxygen, that are ionized multiple times, should be present. And from the atomic physics, we can figure out, if we observe some of these lines in their strengths and ratios, what is the temperature and the density or column density of the intervening gas. And that turns out to be exactly what was needed. These measurements have been done both with Hubble Space Telescope in ultraviolet and also with Chandra X-ray emission in X-rays. And this hot gas has been unambiguously detected in exactly the right amounts. And so this is probably where all those missing baryons really are. But that doesn't tell us where the remaining matter density is. And so next time we will talk about dark non-baryonic matter.